Okay, howdy folks. We're going to continue our discussion, exponential growth and decay. Let's remind ourselves of the finance formula. Okay, we had the final amount equals the principal or the starting amount times 1 plus I, which is the growth rate, percent growth rate, raised to the exponent n, which is the number of compounding periods. This is essentially exponential growth by percent. Okay, so if we're lining this up to take a look, right? We can see how it lines up with our generalized form or generic form of our exponential function. Well, let's take a look at an example. A certain lake was found to have a population of 500 fish. The population counts determine that the population of fish in the lake is growing by 5% per year. So how we define this, instead of using this format, right, you should be able to go interchangeably between the varieties of or formats or varieties of how the different formulas look like, but you see the relative position of each of these terms and know what goes with what, right? So for population, sometimes you'll see it as population as a function of time, because population changes as a function of time, equals A, the initial amount or the initial number of people or things you're counting like cells or fish, the growth rate or the decay rate. We'll do some decay problems later. And X is usually time, or we can sometimes put T instead of X, okay? In this case, my A value is 500 fish. My growth rate is equal to 1 plus 0.05, which is my I value over here, right? Okay, that's my I value, and that's 1.05. And then the time, t, is equal to 1. It's as if, are we dividing by anything? What's the number of compounding? 5% per year, so it's compounding yearly, so it's 1 divided by 1, still 1, okay? So if I plug everything in, population as a function of time equals 500 times the growth rate, which is 1.05 to the first, and that is 525. That should make sense because we start with 500, then we add 5% of that, which is 25. Okay, 25, and that's 525 fish. Let's define each of these. So population as a function of time is the final population or final amount. I think since we're counting discrete elements like cells or fish or people, it's the final population or final number. Okay, A is the initial population or number of items, right? Number. B is your growth or decay factor. We'll do a decay problem later on in this lesson. T is just time. Okay. In the above example, determine how many fish are present after 12 years. I'm going to use my population formula, population growth. That's population as a function of time equals A times B to the T. They want to know the final population after 12 years. The initial amount is 500, so A equals 500. The growth rate is still 1.05, right? And then T is 12 years this time. So that becomes P of T equals A is 500 times B, 1.05 to the T, which is 12. And that equals 898 fish after 12 years. B, determine how long it would take to the nearest tenth of a year for the fish population to reach 2,350. Okay, different kind of problem. Same exponential growth model. This time, the final amount we're reaching is 2,350 fish. The initial population is 500 fish. Our growth rate is still 1.05. Okay, let's fill in our formula. Now I have 2,350 equals 500 times b, which is 1.05 to the t. And t is what we're solving for. How long would it take to the nearest tenth of a year for the fish population to reach 2,350? Okay, this, if we rearrange it, we're going to need logarithms to solve this. Okay, here we go. I'm going to take the common log of both sides. And then just to shorten this work, I'm going to bring that t down and then log of 1.05. Okay, using that power rule, I get, let's finish this up here, log of 2350 over 500 divided by log of 1.05 equals t. Okay, and then so time equals 31.7 years for the fish population to reach that amount, 2,350. Okay. Next page, let's do some more examples here. The university population of a certain town was found to be decreasing by 2.5% per year. If the population was 12,000 in 2012, what will the population be in 2016? This is another population growth problem. Population shrinkage, actually. Okay, a b to the t, but we can use the same equation. So we start out with 12,000 people. The growth rate, okay, it's decreasing. So it's like a decreasing growth rate, or we call like a decay rate, right? So it's 1 minus, well, it's decreasing by 2.5% per year. That is 0.975. So we have a decay rate of 0.975. Time is 4 years. Okay. Okay, continuing here. Just a second, folks, here. All right. Okay, let's fill in this formula. P as a function of t, P of t equals 12,000 times the decay rate of 0.975 after 4 years. That equals 10,844 people. How long would it take for the population, this is part B of the same example, to decrease to half of its population? So let's restate our equation. This time, our final population we're looking at is half of the initial population. So that's times 1/2. So that's the final amount we're reaching is 6,000 people. The decay rate is 0.975, and we're looking for the time. Okay, so let's fill that in, folks. 6,000 equals 12,000 times the decay rate, 0.975 to the t. That is 6,000 divided by 12,000 equals 0.975 to the t. Gonna use logarithms, folks. Okay, let's take the common log of both sides. I'm going to shorten it. I'm going to use the power rule, bring that t out in front. T log of 0.975. Okay, let's solve for t. So that's log of 0.5 divided by log of 0.975 equals t. And then let's evaluate that. That's 27.4 years. Equals t. So it takes 27.4 years for the population to reach half of its initial amount of 6,000 people. Okay. Last example for this part of the exponential growth and decay, a scuba diver's visibility decreases 4% for every meter he descends below the surface. How far will he go before his light decreases to 0.25% of its original value? Okay, let's write our growth and decay formula right here. First, our decay factor, 1 minus, well, it's decreasing. Visibility decreases by 4% for every meter of descent, so it's 0.96. Okay, I'm going to do this for the A value, the initial amount. Well, if you think about it, here's the surface of the water. This is at like this is weird. This is like at a depth of 0 meters, right? And as you go down, you get to like 5 meters, 10 meters, right? So it's like we're going down, like directionally down, right? Getting deeper, and the numbers are going up, right? So I like to think of it this way. We have 100% visibility at the surface. Okay? I'll just say that is equal to 1.0. All right? Use that as your reference amount at the surface. So this is what it looks like here. I'm going to let A equals 1.0. This is the original or reference visibility. Reference visibility. Okay. Okay. Therefore, P of t, the final visibility, it decreases to 0.25% or 0.25 of its original value. So 0.25 of the original value, which is 1. So it's just 0.25. Nice and easy, right? So when I use my equation here, so how far will we go down? So somewhere we go down, 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 down. We're at 0.25 of our visibility. Visibility. Okay, 1.0 visibility. Okay, so we're going to keep diving until we get to that point. So I have 0.25 equals A, which is 1, times B, which is 0.96, to the t. In this case, instead of t, I'm going to say x, right? So it decreases 4% for every meter. So it's not really a time value, but it's in units of 1 meter. So we can treat it like, analogous to a time value, but it's really a distance value. But it's a unit of every meter for 4% decrease, right, in visibility. So I'm going to use x. We don't know what that is. This is the distance in meters. Okay, so let's solve this. That's 0.25 equals 0.96x. We're going to need logs again. So I'm going to take the common log of 0.25. Other side, I'm going to bring the x down with a power law, and it's a common log of 0.96. Okay, and then log of 0.25 divided by log of 0.96 equals x. Okay, and then that is to the nearest tenth, that's 34.0 meters. Oops, sorry, this is a distance value. So 34 meters. So this distance is 34 meters below the surface when the visibility decreases 4% for every meter descended below the surface. It's 34 meters when you reach 25% of the visibility left over. Okay. Next page, folks. Okay, doubling, tripling, half-life. Okay, a single cell doubles every 1 day. What is the growth rate of the cell? So let's take a look at this. So if I have one cell, doubles, so it becomes another cell. Okay, that's in 1 day. This is t equals 0. This is t equals 1 day. What happens at t equals 2? Doubles again. And so on. T equals 2. Okay? What is the growth rate of the cell? So population exponential function. B equals 1 if, let's map this out. B equals 1 if there is no growth. Okay? But if B equals 1, remember we defined this before? There is no growth. If b equals 1, then this is not an exponential function. So b has to be bigger than 1 or less than 1. Doubling, so let's think about this, folks. Doubling means something grows by a rate of, think about it, 100%. Or a factor of 1.0, right? So in this case, it's like our finance formula. When we say something grows by 5%, we do 1 plus 0.05. In this case, when it grows by 100%, we say 1 plus, well, what's the decimal form of 100%? It's just 1. So this is how we get a b value of 2 when something doubles. So growth factor is 2. Okay, let's take a look at an example. A sample of bacteria was found to have 500 cells that doubled every 3 hours. Use transformations to show how the exponential growth formula gets affected. So, if I start with this, so let's start with our growth formula, okay? And we say it starts with 500. Let's do it this way, 500, and then doubling, and we're looking at the time, okay? So if we graph this, folks, let's take a look. So that's 500. Okay. When t is 0, p of t is 500. Okay, so this is t, this is p of t, our axes here. Okay. When t is 1, well, p of t is 1,000. Okay. When when t is 2, okay, just making a little bit more room here, folks. When t is 2, well, p of t is 2,000. So there's our exponential growth right there. Just quickly plot it out. Let's do the other example. Now, how is it being affected when it doubles every 3 hours? Well, let me leave it blank for now. And we say, what happens when we double every 3 hours? What sort of transformation is occurring? Let's graph this and find out. Okay, again, graphing it. If it doubles every 3 hours, so if it starts out, if t is 0, right, no matter what transformation is applied to t, if t is 0, then the initial amount. So I'll start it like this, okay? We know the initial amount's 500, doubling period, okay? Doubling period. And then, oops, let me just make some room here. Double every 3 hours. Okay, so blank t. I don't know what t is going to be multiplied by yet. That's our transformation we're waiting on. But if we double it, so here's 1,000. If it starts out at 500 and it takes 3 hours to double, well, let's do this. 1, 2, and 3. Now it takes 3 hours to double. That's what it looks like, right? So that's P of t. This is t. Well, what kind of transformation does it look like to you? Well, folks, that looks like a horizontal stretch by a factor of 3. So let's write this down. Horizontal stretch by a factor of 3. Okay, horizontal stretch by a factor of 3. Well, what does that translate to as the stretch? That's the stretch factor. Well, what is the value that we replace inside this new function here? Remember, when the factor is 3, then that b value, not to be confused with the b value, the growth factor, the b value, the transformation value, well, that is 3b equals 1, therefore b equals 1/3, okay? 1/3, so where do we put that? Oh, oops, sorry folks. So b equals 1/3. Well, where does that 1/3 go? So right here, okay? So when I replace that, let's see what happens and see if it actually works out. I go 1/3 right here. That's our transformation. This is a horizontal stretch by factor 3. I forgot this, about the y-axis. So you can see it's clearly being stretched this way, okay? Okay, so if I plug it in here, so P of 3 equals 500 times 2 to the 1/3 times 3. Well, that is just equal to 500 times 2 to the 1, and that is 1,000. So 3 hours, t equals 3 hours, you double it compared to the original here, which is you double it in just 1 hour, okay? So a b value, this is a transformation value, just so you don't confuse it with the other b value, which is a growth factor. A b value of 1/3, so I'm talking about this b value, gives you a factor of 3, which means, so in words, let's think about this, which means the time to double takes 3 times as long. So 3 hours versus 1 hour. Okay? So doubling, tripling time, half time, this is the final amount or the number. This is your growth decay factor. P is your period of time. So that's going to be like your transformation that we just talked about right here. So I'm going to highlight it, folks, right here. Okay. That's our transformation that's happening. Okay. Okay, A is our the same. This is still our initial amount or number, and then T is time. Okay, note, very important. So the equation, when we're doing doubling, tripling time half-life, it's the same basic equation, but it gets transformed when we have problems where there are double or tripling time or half time, and that's the transformation that it's undergoing. Okay, here's some important points here. Okay, P of t, come on, P of t and A must be same units. Okay, and T and P must be same units. Okay, let's do an example. A sick patient had a sample of 387 cells taken from her throat. The sample was counted again after 24 hours and found to have 8,012 cells. Find the doubling period of the bacteria to the nearest tenth of an hour. Okay, so let's look at our equation. Okay, P of t equals A times B to the T over P. What do I need? What do I have? So A equals 387 cells. That's what we start with. T equals 24 hours. P of t, our final amount, is 8,012 cells. It's doubling, right? Doubling period. So that's a B value of 2. That's our doubling factor. So when I insert stuff into my equation, 8,012 equals 387 times 2 to the 24 divided by the P value. This looks like something that requires logs to solve. Okay, so I'm going to take the common log of 8,012 divided by 387 equals, well, let me use the power law to simplify that log. Okay, and let's solve. I'm going to simplify some more. Okay, solving for P. Okay, and I get a p-value of 5.5 hours. Okay. Okay, so what does that mean? That means cell population doubles every 5.5 hours. Okay, let's just do a quick handy chart. This is a good way to kind of conceptualize what's going on. So here's my time, and here's my population as a function of time. So at 0 hours, we start at 387. Every 5.5 hours, I'm going to double, so it's 784. Right? Let's see where we get here. So another doubling period, 16 is 11 hours, sorry. We get to 1,548 in cell count. Another doubling period takes us to 16.5 hours. That's 3,096 cells. Another doubling period, 22 hours, 6,192 cells. And then another doubling period takes us to 27.5. That's 12,384. Well, we said 24 hours, we get 8,012 cells. So 24 hours, we get 8,012 cells. Okay, and it's right in between that value right there. Okay, all right. Next page. A radioactive isotope has a half-life of 45 minutes. How long would it take for 480 milligrams of the isotope to decay to 15 milligrams? So let's think about half-life. You might have heard this when we're talking about radioactive decay. So this is the time it takes for a substance. So usually we talk about, so e.g., example, radioactive element, okay, or an isotope. The time it takes for a substance to decay to half of its original amount. Okay, this is, instead of doubling, this is like a halving period. How long does it take for a population to reach half of its original value? So when it decays away. Or this is the period of time for reduction, by factor of 1/2. Okay, so let's define our values of our equation. So P of t equals AB to the t over P. So our final amount that we're decaying to is 15 milligrams. The initial amount is 480 milligrams. Our B value, right, we're decreasing by half, or 50%, so it's 1 minus 0.5, so the B value equals 0.5, or 1/2, okay? We're looking for T, so we don't know T equals. Our halving period, P, is 45 minutes, okay? And then this is like our transformation value that transforms our exponential decay problem. Okay, so let's fill everything in. That's 15 equals 480 times B value of 0.5, T divided by 45. Okay, so what do we got here? 15 divided by 480 equals 0.5 to the T divided by 445. Okay, this one, if you look at it carefully, I get that. 0.5 to the T divided by 45. This 0.03125, we can solve this with a shortcut. That's 0.5 to the 5th. If you kind of play around with the numbers, that's 0.5 to the T over 45. The bases are the same, so I can make the exponents equal to each other. So time equals 225 minutes. So what does that mean? It takes 225 minutes for a radioactive isotope to go from 450 milligrams to decay from 450 to 15 milligrams. Okay, last one on growth decay problems. The half-life of radioactive iodine 131 is 8.1 days. Determine the number of days to the nearest day it would take to decay to 2% of the original level. Okay, so let's write our equation again. Okay, P of t. We're looking for 2% of the original value. Let's start with just a unit, like 2. Okay, if 2% of the original level, then the original level we can say is 100. Okay, so we can just do it in terms of 100. You could say 100%, 200, 2. You can do 1 and 0.02, whatever you like. I'm going to use 2 as the final amount and 100 as the original amount. Then that tells me that's 2% of the original level. So the B value, we're talking half-life, right? So the B value would be 1/2. Okay. And then half-life. So the P value is 8.1 days. Okay, so let's fill in our equation here. That's 2 equals 100 times 1/2 to the t divided by 8.1. Okay, so that's 2 over 100 equals 1/2 to the t over 8.1. That's log of 0.02 equals t over 8.1 log of 1/2. Okay, so that's log of 0.02 divided by log of, let me just turn that into a decimal, log of 0.5 equals t over 8.1. So that's 8.1 times log of 0.02 divided by log of 0.5, and that is my time value. Okay, and then I get t equals 46 days. Okay, so what does that mean? It takes 46 days for radioactive iodine 131 to decay to 2% of its original level.